Now, let us see how the idea of linear regression and logistic regression build up to more complicated ideas such as artificial neural networks. Now, before we discuss artificial neural networks, I would like to discuss two examples that sort of build a motivation to understand how artificial neural networks were born. The first experiment that I would like to discuss is this one. In 1953, Professor Theodore Erisman's group devised an experiment. And this experiment was performed upon his student and assistant, Ivo Kohler. This is also known as the Kohler experiment. So, in the experiment, what the group did was they made Kohler wear a pair of hand-engineered goggles. These were special goggles, such that in the goggles, specially arranged mirrors flipped the light that would reach the eyes, such that the top would become the bottom and the bottom would become top. Here's a YouTube clip that shows Kohler wearing the goggles. In other words, if we were to wear the goggles, we would see this slide, this at the bottom, and the bottom side on the top. So it would be flipped up and down. What's very interesting is after 10 days of wearing the goggles, Kohler becomes so accustomed to this upside down world that he had no problem doing everyday activities. And to him, the upside down world was the normal. And he could do many things very easily. He could walk on a crowded sidewalk. He could even ride a bicycle and do all the day-to-day activities without a problem. The second experiment is a 1978 experiment done by Dr. Martha Constantine Parron's group at MIT. And here's their paper summarizing their findings. Eye-specific termination bands in tecta of three-eyed frogs. So this is a really interesting paper. The bottom line of this paper is what the group did was they implanted an additional eye to a frog. So the frog already had two eyes, and the group added one more eye and connected the eye to the neurons of the brain of the frog, and watched the frog evolve to learn to see with this third eye. And what's interesting is that after doing all of this, the frog, after letting it accept that eye, later learned to see with this eye as well. So it was processing the input from this eye, and the frog's brain was taking these inputs and learning to see with this eye as well. So what's common between these two experiments is that they tell us that our brain is not something that is hardwired to do what we do every day. It's more like this kind of model that has weights in it, and it adjusts its weights or learns from the environment to do what it's supposed to do, or to do what it is being trained to do. We can imagine our brain to be a complex function, way more complex than this, but something that looks similar to this, that has its inputs X. So these inputs, we can imagine the inputs from our eyes, from our senses, and here's the weight that represents our brain, and here's the input, here's the expected output that another part of our brain takes as input to make decisions. And what the brain has to do is update the weight so that these inputs make sense. And this is exactly what happened in Kohler's experiment, where Kohler was updating the weights of his brains in a way to adapt to the upside down world. Similarly, the frog updated its weights in the brain to adapt to see with the new eye. So let's see how neural networks are structured. Neural networks are composed of nodes or units, which are nodes or units connected by directed links that connect these nodes. A link from unit I to unit J serves to propagate the activation or information from I to J. Activation is represented using the letter A, and since the activation is going from I to other nodes, we represent by AI. Each link also has a numeric weight Wij associated with it. So if, let's say we have node I, and then we have another node J, and there's this activation coming out from node AI, and if this node I's activation goes to node J, then this is weighted by this weight Ij. Now this weight, Wij, determines the strength and sign of connection. If this is negative, then the sign may be opposite, and if this is a very small value, then the strength may be small, and so on. Now, just as in the linear regression models, each unit has a dummy input, A naught equals 1. What this means is, if you remember, in linear regression, what we had was output Y equals our input X, weight W1 times our input X plus W naught. And we had this weight multiply our input W, but then this weight was like a constant, a bias that we added, a dummy that we added, and this is what we mean by A naught. So each neuron, if we consider this whole thing as one neuron that accepts input Xi, then this W naught can be considered as a dummy. So this is what's represented by A naught. So here's how a neural network's structure looks like. Imagine that this entire thing is one neuron that accepts input AI, right? So here's our input AI. Then we may have other inputs as well, AI plus 1, AI minus 1, and so on. But for simplicity, let's now consider we only have one input, AI. So this input is multiplied by weight Ij, because the connection is between node I and this current node J that we have, and then we have a dummy weight, dummy input A naught equals 1, which is multiplied by W0J, which is exactly our weight that we add to our input times the weight, also known as the bias weight or dummy input in A naught. Now these are our input links, A1, AI plus 1, and so on, are dummy inputs. So as we saw before, just like in linear regression, we simply multiply the inputs with the weights, add the dummy, and what we get is the input function. What comes out is this input j, I and j is simply the sum of the inputs multiplied by the weight. And then the next thing that we do is we apply some activation function to it, such like something like g, usually a sigmoid or some other nonlinear activations. And then what comes out is a j. That's the activation or output of this particular unit, and that gets transmitted to other nodes that this node connects to. And these are the output links of this unit. So as I just described, each unit J first computes a weighted sum of its inputs. In other words, for each input AI and its corresponding weight Ij, we multiply them and then we sum them for all the inputs that we have, and this gives us the inputs, sum of all the inputs that we would like. That corresponds to the first step within the neural structure. Then we apply activation function G to this sum. So whatever sum we have, this I and J, we apply activation function. Sometimes it can be sigmoid or some other nonlinear activations. Basically activation function of the sum of all our inputs. And this is the second step within the structure of a neuron. So let's look at what happens when we have more than one neurons working together. If we have more than one neurons or even a single neuron whose output serves as the output that we use, then such a network or such a neuron or set of neurons is known as a perceptron network. So in this figure, what we have is these are our input variables. This may be x1 and this may be x2. Here's our neuron 1. This is numbered as 3. So this is our unit 1. Here's another unit, unit 2. So what's happening is these inputs x1 and x2 are multiplying these weights w13 and w23 and being brought together or being sent to unit 1. And this unit receives inputs from both x1 and x2 and sends out its computation or activation. Similarly, we have another unit, unit 2, that also receives input x1 and x2. The first one is multiplied by a different weight, W14, and this one by W24, and it also sends out activations. So such a network where we have a pile of units stacked together, where the output of each unit serves as the output that we want, then such a network is known as a perceptron network. It's basically a single layer neural network. In other words, what we have in the network is all our inputs are connected directly to our output units that we use as outputs. In this case, we only have two outputs. In a perceptron network, we may have anywhere from 1 to any number of outputs that we want. Also, what we have here is two input units. One is two input variables. One is this one node, two node. We also may have multiple inputs all the way to n inputs that we may receive. Now, on the other hand, if these outputs do not directly go to us and these outputs are sent to other units, let's say unit 5 and unit 6, then such a network is a neural network with one hidden layer. In this case, this layer now of neurons, of this layer of units, serves as a hidden layer because we don't use their output right away. We only use the output of the subsequent layers. So this is also a feed-forward neural network, but more popularly known as the perceptron network because it only has one layer. But if we extend the idea and add layers such that we have hidden layers, then becomes a neural network. Now, the perceptron network that we just saw, that is a network with only one layer of neurons, has some limitations. Let's take a look at that. What I have in this plot is 4 data points. Here's the first data point, second data point, third data point, and the fourth data point. Imagine these to be nuclear explosion and earthquakes. Let's say the black dot represents nuclear explosion and these 4 represents earthquake. What we would like to do is build a classifier, a model that can classify these 2 data points. Clearly, if I find this classifier, this line, I can use it to classify these 2 sets of data points, right? Everything below this line is earthquake and everything above is nuclear explosion. Let's say I flip the case and I have the data points like this. Now these 3 data points represent nuclear explosion and this one represents earthquake. Once again, I can find a classifier like this that I can use to classify the data correctly into these 2 classes. Let's say I have the data in this way. In other words, now I have nuclear explosion sitting like this, 2 data points, nuclear explosion, and I have earthquake sitting over here on 2 sides. Now, let's try to find a single line that can classify these data points. So if I find a line like this, it can classify these and these correctly, but this one not correctly. If I find a line like this, it can classify these 3 correctly, but not this one. So no matter how I draw my line, I cannot correctly classify these 4 data points. And that's exactly the limitations of perceptrons. With a single layer of neurons, whatever linear classifier that you build cannot classify the data points which are not linearly classifiable. Now, the neural networks that we saw are these units of neurons that takes some input, certain inputs, and then sums, applies activation, and produces an activation, can be connected in distinct ways. The most common way to connect them is known as feed-forward connection. That is, connection in only one direction. And such a connection forms a directed acyclic graph. So the one that we saw was, here's, let's say, our input, let's say xi, and second x2. Here's our first set of neurons, and then let's say we have additional units. So all of these get sent to the first layer, um, and these again further send their inputs to the second layer, and so on. And let's say we have one unit at the end that takes all the inputs and makes the final predictions or final activations come out of this. So what we see is we have a directed graph that goes from one side to the other side with no cycles in it. Each node receives input from the previous nodes, upstream nodes, and delivers output to the downstream nodes, nodes that are towards the output. So here's our output and here's our input. Also, the feed-forward network represents the function of its current input. If you remember this equation, this output A can be expressed in terms of all the previous inputs. And this has also no internal state or other than the weights themselves. So the only thing that is also preserved in this network, or what we have in this network, is these weights that connects neurons or units that are units where the input is going from one unit to the next one. The second way of connecting these units is a recurrent connection. And in recurrent connections, what we have is the output is sent back as its own input. So let's say I have input 1, another input 2. So these are x1 and x2. Let's say I have two units. So these get sent to these, and then we also have connections to output. And let's say this is our output. We also have cross connections, so that we have like this. So this would be a feed forward setting. The first kind. Now in recurrent neural networks, what we have is we have connections within these nodes. So there's a weight that it multiplies. So the output of this node gets sent as the input to this node again. So more appropriately, something like this. This means that now these weights, if this is a 1, the output gets multiplied by the input, keeps getting added to the input itself. Such a network can form a dynamical system where the weights can continuously update, which may reach a stable state or even exhibit oscillations where the network might loop into certain situations, or even exhibit chaotic behavior such that the weights, the activations of each node always become a 0 or always become a very high value, and so on. Moreover, such recurrent networks output depends on its initial state. So if these initial weights, that is these recurrent connections, were all 0, then that means your network may never produce anything more than 1. And because of these initial weights, if it is 0, it acts in a different way. If it is 1, it acts in a different way. We consider recurrent networks to also have short-term memory, because they already have weights that connect or that sort of act as a memory, or serve as a pre-learned weights or connections between the nodes itself, the outputs of the nodes. These also make them very interesting models of the brain, because in our brain the connections are not necessarily only feed forward. We have all kinds of connections, but because of these cyclic connections, it makes us very difficult for us to understand how these networks operate, how to train them, and how to effectively use them. Most of the machine learning applications only focus on feed forward neural networks, and that's what we will do. So let's take a look at a feed-forward neural network and understand how the output at a particular node is calculated. What we have in the picture is a neural network with 4 units. This is unit 3, unit 4, unit 5, and unit 6. These are not actually neural units. These are our inputs, x1 and x2. If we had a data that had 2 columns, then this would be our first column, and this would be our second column, x1 and x2, right? We have weight W13 multiplies our input, sends it to our first neuron, unit 3. We also have the second input, x2, multiplying with weight W23 and being sent to the same node 3. So this receives x1 times W13 plus x2 times W23 plus W03, and it sends it output to the second unit 5 multiplying with W53, same with unit 4, and so on, and from here we get the output. So this is activation A5 and this is activation A6. So let's see how this gets broken down. So let's try to compute the equation or calculate how A5 may be calculated. So A5 is activation function G applied to sum of all of these inputs. So these inputs are nothing but this: W05, the first bias, W35 times A3, W3 times activation A3 at this node, and W45 times activation of A4, W45, this weight, times the activation of this node A4. Now, so this is one value. There is nothing we have to do about this. Now this A3 is activation function F applied to the sum of all of these inputs. So this is A3 is activation applied to W03 plus W13A1, W13 X1 or A1 if they consider this as activation 1, and W23 times A2. So you get the idea. This is how we have activation A4 as well, and the final equation, this expression for A4, gives us a way to calculate the output at unit 5, A5. Now, depending upon how we connect the neurons, neural networks can have various structures. What we saw so far is a perceptron network. So these are your input nodes. These are your inputs. We only have one neuron, one unit that serves as your output unit. In feed-forward neural networks, what we saw was these were hidden units. These are also neurons, but they receive the input and send it out to the subsequent units, and output comes out of this unit. So these are feed-forward neural networks. If we have many hidden layers like these, then those become deep feed-forward neural networks or deep neural networks. If we have recurrent connections between or cycles in our hidden layers, then those serve as recurrent neural networks. There are many variations to it. If the recurrent connections are done in a different way, in a specific way, those serve as LSTMs. For another settings, those may serve as GRUs. If they're connected in a different way, they may serve as a radial basis network. So there are tons of other networks that are popularly used these days based on how the connections between the units are made. Now, another topic within the topic of learning, which is very interesting to learn, is ensemble learning. Now, the idea behind ensemble learning methods is to use a collection or ensemble of models or hypotheses from the hypothesis space and combine their predictions to make a more powerful model. A popular technique within ensemble learning is known as boosting. So now, to understand the idea behind ensemble learning, let's take a look at this example. Say, for example, these minuses and pluses represent our data in two classes. Let's say the minuses are earthquakes and the pluses are nuclear explosions that we would like to classify. And we see that nuclear explosions are all clustered in the center, and we have earthquakes or these negative data points spread around of this nuclear explosion points. Now what we would like to do is design a classifier that can classify the data into two classes. So let's say I start with this kind of model, model 1, a linear line that can be used to classify these two data points. Now you will notice that this line can classify these data points correctly and these data points correctly, but these are falsely classified as positive data points. So let's say I add another model, this line, model 2, to see if I can do better. With this model, what we can do is I can classify these correctly. If I consider this as a plus, I can classify these also correctly, these correctly, but these and these are classified incorrectly. However, if I combine model 1 and model 2, what we see was in model 1 we classified this correctly, but not these and these and these. In model 2, we classified these correctly and these correctly and these correctly, but not this. So both of these models can classify everything else correctly, but miss to classify the data points in this. So let's add another model, model 3, as this line that can classify this also correctly. Now if we combine these three models, model 1, model 2 and model 3 correctly, appropriately, then we can imagine that the combination of these three models can correctly classify all the data points into their proper classes. And a specific algorithm within the topic of ensemble learning is boosting. The idea behind boosting is it's a specific algorithm that uses the idea of ensemble learning. The idea behind boosting is you start with model 1, classify the data points, and those that are classified you forget them, and those that are not correctly classified you try to build another model and keep repeating this over and over until you can classify all the data points correctly. In summary, what we saw in this chapter is if there is feedback available that where we have the correct answers, for example inputs, then such a learning is known as supervised learning. The task here is to learn a function that this hypothesis function H(x) that can give our output y. We also discussed that if we are trying to classify, if we are trying to build a function or learn a function that can classify data points into 2 or 3 classes, then that's a classification problem. And if we are trying to predict a continuous value, then that is a regression problem. And not all errors are equal. A loss function is something that tells you how bad each error is. We also saw that the idea of using logistic regression replaces Perceptrons' hard threshold with a soft threshold defined by the logistic function. And we saw that the gradient descent algorithm works well even for noisy data that are not linearly separable. Overall, we understood that neural networks represent a complex nonlinear functions with a network of linear threshold units. At the end, we saw that ensemble methods such as boosting often perform better than individual methods. Thank you.